So finishing up the reactions of carboxylic acids into different functional groups. Last time we left off with conversions of carboxylic acids into esters. Here we're going to be looking at the conversion of carboxylic acids into amides. And so this is actually kind of difficult because amines and amides, for example, are organic bases, right? So carboxylic acids act as organic acids, and amines act as proton acceptors or Lewis bases because they lone pair donors. So these act as organic bases, which means that they would convert a carboxylic acid into an unreactive carboxylate ion, right? So kind of like the ion, right? So if they convert it, they deprotonate carboxylic acid, it becomes less reactive. And so usually to circumvent this, a carboamide is added first, and then an amine is added after that. And so we initially get attack of the carboxylic acid proton. So if this is our carboxylic acid here, and then we have a carboamide, which looks like a double bond nitrogen right here. And so the way this kind of works is the carboamide doesn't have a proton in it, so it can't really act or abstract protons from the solution. Instead, directly attack, so this is going to have some R groups over here as well. We'll instead directly attack the, oops, sorry, I put this in the wrong. It's going to be an imide, not a, right there. So this lone pair is directly going to attack this proton and create the carboxylate ion directly. And then once we have that, then the carboxylate ion can actually do nucleophilic attack on the carboamide. And so this is going to go to the carboxylate ion, which is negatively charged, which will then attack the carboamide. This is going to be positively charged now. R. This will attack this carbonyl carbon, which is going to be pretty strongly electrophilic because it's double bonded to a nitrogen down here and another R group. This creates another complex where this can undergo nucleophilic acyl substitution from an amine directly, right? So this kind of creates a pseudoester. NHR, double bond NR. And so now we can get the amine coming in, and the amine can be a secondary or secondary or primary amine. And we'll talk more about that in future lectures, the actual classifications. We'll have this as a primary amine. So this lone pair is going to attack the carbonyl carbon, which is usual in our nucleophilic acyl substitutions. And then this will give us our tetrahedral intermediate that we usually see. H, and then this is going to have a plus sign there. O minus O, and then this whole carboamide complex that's been created now. R, like that. And then this is going to be undergo a big rearrangement with acid that's going to be in solution to then generate our amide here. All right, so this next step is going to be a large one, a large concerted mechanism, and we're going to have HA present. I'm doing this in red just because it's easier for this to see. You're going to get attack of the proton from the pi system in the carboamide structure. This is going to abstract the oxygen from the tetrahedral intermediate, and then the tetrahedral intermediate is going to reform its sp2 hybridization with electrons moving down. And so when this happens, we'll end up with RC double bond O N H plus, and then R prime. And then this plus on the amide if we have this conjugate base here, or whatever the acid was, that can come and attack one of these protons, and then it'll get rid of the proton, and that'll be our final structure. So this is a mechanism for converting a carboxylic acid into an amide, and so this is actually really important for the synthesis of proteins in a laboratory. That means like in a benchtop setting, you're actually probably going to synthesize these, with genetic modifications these days. So you take advantage of the cellular machinery and modify a genome to then complete that. Carbamide that we use a lot of times for this, which is the one I just showed, is going to be amide DCC. So this is what you would see in the reaction arrow. So what this would look like is if, let's say we had two different amino acids. Then one amino acid has its N-terminus. We'll talk more about these when we get to them. Then we have the alpha carbon. This is our R group, which gives the amino acid its identity. And then we have another amino acid. It has the same backbone. Here's R1. And its C-terminus, like this. We put it in DCC, and we get the joining of the carboxylic acid, carbonyl, here to the amine side, or the amine side of the other amino acid. And so ultimately what we'll get is H2, alpha carbon, carbonyl carbon, the amide functional group, which forms what we call the peptide bond here, R2, in the second carboxylic acid group, R2, sorry, and then this would be R1. All right, so this would be our product for the reaction in a laboratory setting using our carboamide. Okay, so that's how we're going to do the conversion of carboxylic acids into amides. The next thing we'll talk about is the reduction of carboxylic acid, and so we're reducing that into going to be forming carbon-oxygen bonds and breaking carbon-hydrogen bonds. And so one of the interesting things here is we usually have our tetrahedral intermediate, but the hydride ion is actually slightly basic. So the reaction mechanism takes place with the negatively charged carboxylate, sorry, not negatively charged carboxylate, but a deprotonated carboxylic acid, a deprotonated carboxylic acid. So it'll be something like this. We add our strong reducing agent, which would be probably lithium aluminum hydride, and our hydride ion is going to be our nucleophile. This is actually first going to convert this into a carboxylate ion because it's negatively charged, and this gives us a different intermediate that'll be used instead of our usual tetrahedral intermediate. What ends up happening is we get a stabilization of a dianon structure, which is going to be created from the nucleophilic attack of the hydride on the carbonyl carbon here. So lithium aluminum hydride, and the role of this is to stabilize the dianon. All right, so it's strongly reducing because it creates this hydride in solution, but it also stabilizes the dianion. And so this is going to attack the nucleophilic, or the carbonyl carbon. It'll move the electrons on the top here, and then we'll get this dianon structure. That was the H that just attacked. We have two negatively charged oxygens here, and those are going to coordinate with the aluminum, right, because this is a good Lewis acid or electron acceptor. And so this coordinates with both of those, and this is going to go through a type of rearrangement that abstracts one of the oxygens. Let's make this a different color. So this is like, it's not a real covalent bond, but a coordination. And one of them is going to form a bond with the aluminum, and then the pseudo electron density from the other one is going to reform the carbonyl. And so after that, we get our final product, which is our aldehyde, right? And so our aldehyde is a reduction of a carboxylic acid because we have lost this carbon-oxygen bond and we formed this carbon-hydrogen bond, right? And so actually, I realized I wrote this wrong and probably said this wrong. We're forming carbon-hydrogen bonds when we're reducing. I wrote what I wrote is for reduction, or what I wrote is for oxidation, and then we're breaking carbon-oxygen bonds, right? So it's the opposite of what we did when we were talking about oxidation, right? So the final product is going to be an aldehyde. You can also do this with boron or borane, which is BH3, and THF. This is usually preferred. It'll reduce it all the way until borane and THF, and this is usually preferred in a laboratory setting. And then you protonate with acid. This is preferred in a laboratory setting just because of its ease of use and safety. Lithium aluminum hydride will kind of reduce anything it comes in contact with, and this will go all the way to a primary alcohol, right? And it's important to say that it goes all the way to a primary alcohol because it's always going to be primary because we're starting with the carboxylic acid, which is the terminal end of a molecule. And then, so here we have p-nitrophenolacetic acid, O2N, and if we were to reduce it with borane and THF, and then add acid afterwards, this would convert this into a primary alcohol because that's at a terminal end of a carbon chain. So we have something like this. We get an OH where the carboxylic acid group was, and then 2 hydrogens there as well, right? So this would be a primary alcohol. So with aluminum hydride, you form a aldehyde, and if you use borane and THF, that'll give you a primary alcohol. But the same idea of breaking carbon-oxygen bonds and forming carbon-hydrogen bonds stay the same. You just go one step further, and you get rid of the aldehyde hydrogen there. Okay, so we'll end that for today, and then we're going to talk about acyl halides in the next lecture.